All right, so we're going to look at another type of series where we can actually find exactly what it sums to. And let me remind you, the idea for geometric series was that we first found a formula for the partial sums, and then once we knew how to compute the partial sums, we could just take a limit to find the sum. And it's not always going to be possible to find a nice simple formula for the partial sums, but we will see that there are certain other types of series where it is possible. And the one that we're going to look at now is what's called a telescoping series. All right, so rather than giving you sort of a general framework, let me just give you some examples. So let's start with the sequence an equals ln of n over n plus 1. Okay, and what we would like to figure out is what is the sum from n equals 1 to infinity of an. Okay, so we want to find how do I sum the terms in this sequence? In other words, does this series converge or does it diverge? And if it does converge, what does it converge to? All right, so let's start by writing out some of the terms in this series. We'll start with a1. So if we plug in 1, we'll get log of 1 over 2. And the second term would be log of, now we'll plug in n equals 2, so we'll have 2 over 3. And a3 would be log of 3 over 4. And you get the idea. Each term is going to have the power in the numerator is going to, or the constant in the numerator is going to be 1 higher than the constant in the denominator. Now, unfortunately, although you could write this out as log 1/2 plus log 2/3 plus log 3/4 and so on, that doesn't really give us any clues as to how to actually figure out what the partial sums are approaching. But if we get a little clever with our log rules, we can actually simplify this, because notice that the log of 1/2, well, recall that the log of a over b is equal to the log of a minus the log of b. So this can be written as the log of 1 minus the log of 2. And a2 can be written as the log of 2 minus the log of 3. And a3 can be written as the log of 3 minus log of 4, and so on. Okay, so now that we've got our individual terms mapped out, let's think about some partial sums. S1, the sum of just the first term, is just a1. So that's log 1 minus log 2. S2 is the sum of the first two. And that would be L1 minus L2, log 1 minus log 2, plus log 2 minus log 3. And notice the log 2's are going to cancel. And so we'll have log 1 minus log 3 that stick around. And some of you may have noticed that log 1 is something we can simplify as well. That's actually just 0. But I'm going to leave it there for now, just so that you see the pattern. S3 would be a1 plus a2 plus a3. And that's got to be log 1 minus log 2 plus log 2 minus log 3 plus log 3 minus log 4. And again, we have some cancellation that's going to happen there. The negative log 2 cancels the positive log 2. The negative log 3 cancels the positive log 3. And we're left with log 1 minus log 4. And at that point, I think the pattern is pretty clear. We should be able to find a nice formula for it. Notice that Sn, well, each of these partial sums has a log 1 in it, minus another log, and the second log is always a number 1 higher than the subscript. So when I had S1, I had a 2 inside the log. When I had S2, I had a 3 inside the log. And so when I have Sn, I should have an n plus 1 inside the log. All right, so the partial sum, and now I will simplify. Log 1 is actually equal to 0. It's just going to be negative log n plus 1. And so if I want to find the total sum, now that I know of nice simple formula for the partial sums, I can just take a limit as n goes to infinity to see what happens if I add up all of them. Not just 3 of them or 4 of them or n of them, but rather all infinite number of terms. And in this case, we'll see that we're going to get negative infinity. Logarithm, if you plug larger and larger numbers into it, will go off to infinity, and with a minus sign that makes it negative infinity. Okay, so the reason that we call this a telescoping series, at least the way that I think about it, is it reminds me of those old telescopes that used to collapse on themselves. So I apologize for my limited art skills, but essentially what we see is that we've got this long collection of things, and you can think of this as A1, A2, and A3. But when you press it down, when you squash it together, ultimately you just have to think about the front and the back. All the other ones end up collapsing down on top of each other. And that's really what this type of series does algebraically. We have a whole bunch of cancellation, and only the beginning and the end ultimately stick around. Okay, so this would be an example of a divergent series. And it turns out that this is another useful counterexample. You remember that we said earlier the nth term test said the following: if an does not go to 0, then the sum of an off to infinity diverges. Well, here, if you look at our original terms, they are actually going to 0. You can check because when n gets large, the numerator wants to go off to infinity, the denominator goes off to infinity, and so this looks like infinity over infinity, which is indeterminate, but we can actually simplify that. We have the terms that we're dealing with were log of n over n plus 1. But if we multiply this by 1 over n on top and bottom, what you'll get is log of 1 over 1 plus 1 over n. And as n goes to infinity there, you can see that this thing wants to approach 1. And so we're approaching the log of 1, which is 0, which means that the individual things that we were adding up, they go to 0. So we're adding up smaller and smaller terms in the series, just like the harmonic series 1 over n. But that doesn't necessarily mean that the sum converges. In fact, we just proved that this is a divergent series. Even though the things we're adding up are infinitely small, they become small slow enough that we still have an infinite amount of stuff when you accumulate everything. All right, so I show you that to remind you of the nth term test. The nth term test can show us divergence. In this case, though, the nth term test was inconclusive. Right? We got 0, so it doesn't really apply. It only tells us something if the terms do not go to 0. But because this was a telescoping series, we were able to get around that and actually find the answer a different way. All right, let's try another example. Let's look at the series made up of the following terms: 1 over n plus 2 minus 1 over n. And again, from n equals 1 to infinity. All right, and so as before, we're going to start by trying to find an expression for the partial sums. And then once we've got the partial sums down, we'll take a limit to see what the sum approaches. And so we'll first compute the individual terms and then the sums. A1 would be equal to, 1 over 1 plus 2, so 1/3, minus 1 over 1. A2 would be equal to 1 over 2 plus 2, 1/4, minus 1 over 2. A3 would be equal to 1/5 minus 1/3, and we'll keep going. A4 is going to be 1/6 minus 1/4. A5 would be equal to 1/7 minus 1/5, and so on. All right, so let's find our partial sums now. Those are the things we're adding up. The partial sums mean we add up all of them up to the subscript. So in the first one, we're just adding up a1, and so we'll get 1/3 minus 1 as before. The second partial sum would be a1 plus a2, so the sum of the first two. And so there we'll have 1/3 minus 1 plus 1/4 minus 1/2. And unfortunately, there's no cancellation there. So we can't simplify that any further. We could write it as a single fraction, but I'm going to leave it that way because we are going to see a pattern here. It just, we need to look a little bit harder. All right, so the next term will be 1/3 minus 1 plus 1/4 minus 1/2 plus a3, which is 1/5 minus 1/3. And there we go. Now we have this 1/3, and the minus 1/3 is going to cancel. All right, so we'll keep going. So the next one's going to be the sum of an up to 4. And so we'll have 1/3 minus 1 plus 1/4 minus 1/2 plus 1/5 minus 1/3 plus 1/6 minus 1/4. And notice the 1/3s cancel. Oops, that was a 1/5. Let me fix that. The 1/3s cancel, and the 1/4s cancel now. All right, so I'll write that a little simpler. We have -1 minus 1/2 plus 1/5 plus 1/6. And we could actually write this down. S5 is going to be 1/3 minus 1 plus 1/4 minus 1/2 plus 1/5 minus 1/3 minus 1/3 cancels plus 1/6 minus 1/4, and the minus 1/4 cancels. And then the next term would be 1/7 minus 1/5, and that's going to cancel out 1/5. And so we see that there is this pattern of cancellation. It's not quite so nice as the previous one, but there is a clear pattern if you write what you have left. We have -1 minus 1/2, so that's exactly the same. But what things have not canceled? We have 1/6 and 1/7. And if you look at S3, we had, didn't give myself much room here, we have -1 minus 1/2 plus 1/4 plus 1/5. And in S2, we had -1 minus 1/2 plus 1/3 plus 1/4. And you see, so that we always have -1 minus 1/2, and it's just the last two terms that are changing. And if you look at the subscript, we had S2, and here we have 3 and 4. So the two fractions we added were 1 and 2 integers higher than the subscript. And that's going to actually be true for all of these. For S5, we had 1 higher in this denominator and 1 higher in that one. And so our partial sum, the nth partial sum, is going to be, if we describe the pattern, it would be -1 minus 1/2 plus 1 over 1 higher than the subscript plus 1 over 2 higher than the subscript. Oh, not 3, how about a 2? All right, and that's the nth partial sum. If we want the total sum, we just need to figure out what those things are approaching. And at this point, notice that term, its denominator is getting bigger, and the numerator is staying the same, and the same thing would be true for the next one. So those are both going to approach 0, and we'll be left with -1 minus 1/2. Okay, so this was also a telescoping series, but instead of having to go out one term to see the cancellation, you just had to go out 2 terms to start seeing things cancel. But the same approach still applied. We wrote down a bunch of partial sums, we identified the pattern, and then we took a limit to see whether the series converged. All right, one last example for you. let's look at the series an equals 1 over n times n plus 2. And right off the bat, you notice we don't have a difference here like the previous example. So if we were to proceed without any simplification, we're going to find that it's not obvious what's happening here. The pattern is going to be a little too complicated. But what I want you to notice here is we could imagine splitting that fraction up into two pieces using partial fraction decomposition. And if we could do that, we might be better able to see if there's cancellation between terms. So let's try partial fractions here. See if we can split that up into two fractions to just get a different perspective on the original sequence. So as before, as we did with our integration problems, we'll try first of all to get rid of the denominator. We can write this as 1 equals a times n plus 2 plus b times n. And now we can that needs to work for every value of n. So it should work for, say, n equals 0. It should work for n equals negative 2. It should work for everything. All right, so let's try n equals 0. Then we'll have 1 equals 2a. So a must be 1/2. And if we try n equals negative 2, and I'm choosing those particular values to try to cancel out one of these two terms, we'll get a times 0, when we plug into the first term, plus b times negative 2. So b must equal negative 1/2. And so this must be just 1/2 times 1 over n minus 1 over n plus 2. Or better yet, we could write this as negative 1/2 times 1 over n plus 2 minus 1 over n. Now I say that's better because notice that's exactly what we studied in the previous problem. Right? We were looking at this sequence where the terms were 1 over n plus 2 minus 1 over n. And here we have the same thing. The only difference is the extra factor of negative 1/2. And so what that means is if each term in this sequence is negative 1/2 of the terms in the original sequence, well, we should be able to factor out that 1/2. And so we could say that the sum of 1 over n times n plus 2, we can write that as the sum of negative 1/2 times 1 over n plus 2 minus 1 over n. This can be factored out since it's just a constant. And if we look back to the previous problem, we know exactly what that is. That sum we showed was negative 1 minus 1/2. And so our answer is just going to be, let's see, this is negative 3/2, and so we'll just get 3/4. Okay, and so there we go. We've shown that this converges. The limit needs to be 3/4, and that's because we essentially turned it into a problem that we had already solved by using partial fractions. So what are the takeaway messages? Well, there's really 3 steps to these sort of telescoping series problems. First step is write down the partial sums. Next, we need to identify the pattern. And second, and lastly, we take a limit of the partial sums to see if the series actually converges or not. And sometimes, I'll add this sort of as a step 0, we may try to simplify. First, we use log rules for the first example. We use partial fractions for the last one. But sometimes writing the individual terms with a difference makes it easier to see the cancellation that does actually occur. All right, so we will stop here for today and move on to the next chapter next time.